24 hours plus, the three of us are going to talk about various aspects of MPI. MPI part of this course is long, but not long enough if we were not to assume that most of you have done some MPI programming. We know that because we were some of the people who looked at your applications. So we know that you're qualified, and in some cases you have as much MPI experience as we do. But at least at the beginning, rather than talk about the parameters to codes and do tutorial stuff, we'll try to focus a little bit on the concepts that are behind MPI, maybe causing you to think about things that you've already used in a slightly different way. Especially tomorrow, we're going to focus on scalability. That is, MPI was designed more than 10 years ago, but it's changed over time. And some of the scalability issues were not apparent 10 years ago. MPI has evolved to address them now. What are those things, and what are some of the things that were actually designed into MPI at the beginning that allow scalable use that may not have been used so much when it wasn't necessary. So we're going to do some code walkthroughs and some exercises. At the end of this talk, if there's time, I'd like to walk you through downloading one implementation of MPI onto your laptop itself or onto your cluster back home or whatever, so that you can run some local experiments on your machine of choice. And MPI-CH has some advantages beyond what the commercial MPIs have. But also Vesta will be available, and I'll talk a little bit about running MPI on that. So for the next hour, I'll talk a little about MPI concepts, the historical course of MPI, MPI 1, 2, and 3. I'll focus quite a bit on blocking and non-blocking communication in order to get a sort of a feel for how those simple MPI 1 concepts, why they are the way they are, and how to use them. And then we'll talk about MPI-CH and installing it on your machine and running some examples. We'll do that after dinner. Well, maybe we could get started with the install before dinner, and then everything will be all set after dinner. Tomorrow morning, Bill Gropp will talk about scalability issues. What are the obstructions to obtaining scalability in MPI programs, and how can you get around them with some of the built-in MPI tools? And thinking more deeply about inadvertent communication delays that you might introduce into your program and how to avoid them, minimizing data motion, using MPI data types. So some of the more advanced parts of MPI. And also some topics in collective communication. Tomorrow afternoon, we'll focus on remote access, remote memory access. That's the put and get operations that were introduced in MPI 2. And I'll return and talk a little bit about the MPI 3 standard, not in great detail, but in terms of the new ideas that are in it and the new capabilities. MPI-CH implements almost all of the MPI 3 standards, so you could start trying some MPI 3 ideas right away. And near the end of tomorrow, we'll talk about process topologies, which are involved in the neighborhood collectives, which are one example of a very useful MPI 3 concept. And we'll do some work with the Halo Exchange example that Bill will talk us through, working through tomorrow night. This slide is probably unchanged in quite some time. What is it? So it's a library. It's a library interface standard specification. So it isn't a specific implementation. It's a specification for a set of library calls. And it starts by implementing the classical message passing model, but as Mark said in his talk, it's evolved to actually be capable of implementing a number of different programming models when you think of them as models the way Mark was talking about them instead of specific languages and libraries. So MPI 1 was defined in 1994. Bill Gropp and I are grizzled veterans of that process. It was a group of parallel computer vendors and computer scientists and application developers, and I think the idea that the development of the standard was open and equally participated by all these groups was very helpful. We met every 6 weeks, and I think I've often said that one of the key ingredients behind the development of the standard was what a wretched hotel we stayed at in the remote suburbs of North Dallas. We met, there was absolutely nothing there. There were no restaurants, nothing. We met every 6 weeks, which was a lot. So it was quite painful, and that has a real advantage. We made it completely open. Anyone who wanted to come in the whole world was welcome to join the process. But anyone who wanted to come and watch pretty much lost interest. It was just too awful. So if you're going to develop a standard, don't do it at a fancy hotel in Hawaii. You'll get too many people involved. So actually the implementations appeared fairly quickly. At that time there were many different message passing libraries. And now we take MPI for granted as part of the system software on almost any machine. And there are free and portable implementations as well as the commercial ones. Bill and Rajiv and I have been involved in MPI-CH. OpenMPI is another perfectly serviceable, portable and free implementation. Just to see sort of how things developed, the standard was published in 1994, and it had the things that you're most used to: basic point-to-point communication, collective operations, several new ideas that were not in the existing implementations, things like communicators and data types. Right after MPI came out, there were several people who said, oh, it's way too big, it has too many functions, and equal number of people said it's too small, it doesn't have all these other things that we need. So MPI 2 added things, particularly parallel I/O, that people felt were really missing in MPI 1. Also remote memory access to put and get operations, which we'll talk about quite a bit. Dynamic processes, which are not used so much because it's difficult to make them portable to every environment. I would say they were probably mainly a response to the fact that PVM was the most popular parallel programming library at the time, and people used them a lot. Also introduced thread safety support and C++ bindings. And then it was sort of frozen for 10 years, which I think was a good thing, and let application developers and implementers get used to it. Process got started up again about 2008 with some veterans from the original MPI forums and some new people. If you ever hear about these details, 2.1 was minor clarifications and bug fixes to the standard that had become apparent during the preceding 10 years. And a year later, we made some small updates and some additions that were the most in demand. And MPI 3 has major new features and additions to MPI. MPI 2.2 is backward compatible all the way back to MPI 1. There are a couple of changes in MPI 3 that break total backward compatibility, but with good reasons, as we'll talk about. Let's begin talking about some of the MPI concepts, sort of starting from scratch here. So what do we mean by a process? That's an address space. This is very important because MPI is all about address spaces. It's an address space and a program and one or more threads of control, and a thread has a program counter that says where in the program is it executing, and a stack of the memory that's allocated on the stack and the parameters to the subroutine calls. Those are separate for each thread. And the threads share the address space except for the stack part. And this has advantages and disadvantages. And so you can think of a process as an old-fashioned Unix process. That's just a single-threaded process in this definition. And that's the way we were really thinking of processes in MPI 1. We were thinking of old-fashioned Unix single-threaded processes, and we identified these processes by their MPI rank. Take a good example of the sorts of things that standards committees worry about, as should the ranks start at 1 or should they start at 0? You can imagine months of discussion over items like that. The thing about these issues like this is what I remember about the process. I vividly remember how violent the argument was on some of these issues, but I can't remember which side I was on. That is, in the long run, working over time, almost all the decisions that we made became second nature to us, and it seems like it could not be any other way. I thought I'd note here that MPI was never, even from the beginning, SPMD. I've heard some people say, well, MPI is for SPMD programs, single program, multiple data. Right from the beginning, you could always have completely different executables on different MPI ranks. Then in MPI 2, semantics were defined that let MPI processes be multi-threaded. That is, one had to define what did it mean if two threads executed MPI calls at the same time. And the various aspects of thread safety will be talked about later in the course when we get to hybrid programming. Let's bring out this idea of address space a little bit more. Sequential programming is one single threaded process. Parallel programming occurs in multiple ways. This is sort of even up above the level that Mark was talking about. We can have one process, that is one address space with multiple threads. They share memory in that address space. That's parallel programming. Or we can have multiple single-threaded processes. That's the MPI 1 model of things. Or I would say MPI implements that particular parallel programming model. Or we can have multiple multi-threaded processes. That was allowed by MPI 2, and we often call that hybrid programming, and there will be a talk later this week by Bill Gropp on mixing MPI with multi-threaded programming. So here's, this next bullet is an opinion. Shared memory parallel programming is harder than it looks. So that, to me, self-evident to anyone who has tried debugging a shared memory parallel program. It can be very difficult because it's hard to, when multiple threads have access to the same variables in the same address space, it's very difficult to tell exactly what's happening. And to the message passing bigot, like me, it's because of the shared address space that's giving you all the trouble. At the same time, processes and threads have to communicate, otherwise you've just got a handful of sequential programs, and that's not what we're talking about here. What is MPI for? MPI for, what MPI is for communicating between address spaces. It's for moving data from one address space to another. The reason we want to do that is because we actually don't want to share memory, even from the programming model, programmer convenience point of view. So the reason this is an opinion is many people would say shared memory is much easier, and it's certainly the case that some problems are more easily expressed that way, but wait till you have a bug. Here's how MPI communication works, and I'm assuming that you're all pretty familiar with this. So if we think of the communication among address spaces as the thing we're really targeting, what MPI does is say, okay, process 1's got this address space, process 0's got this other address space, and for a very limited time and in a very limited piece, I'm going to open up my address space to the other guy. So I'm not going to open up all my address space for all time. That's shared memory. I'm just going to squeeze that shared bit down in both space and time. So you do an MPI receive, you take a very small, relatively speaking, piece of memory, and you say, okay, it's okay for the other address, for the other process to write in there. In MPI, you can say it's only allowed for this particular rank to write in there. So you're allowing this communication, but you're limiting the opening up of your memory. You're limiting it very much in space and time, and that's the communication buffer. Similarly, on the send side, that process is saying, okay, it's okay for the other guy to read out of my memory, but only this little bit of memory and only for the duration of this subroutine call. Now you can expand that in time by using the non-blocking operation, so that's what I have at the bottom here. So when you do the I receive, you open it up, and then you continue on, but you continue on with the knowledge that somebody else might be writing in there. Similarly, if you do a non-blocking send, you notify the system that this is the data that's going out, and then you are aware that the system is reading that until you do the wait. So what the non-blocking routines do is they just open up the window in time in which you allow access by other processes to part of your address space. So let's talk a little bit more about blocking and non-blocking communication. So this is sort of what I was just saying. I receive exposes part of its address space to what I'll call the system, whatever's not the application program. It's the MPI implementation combined with the operating system, combined with the communication hardware in the system and so forth. It's all the stuff I don't know about as an application programmer making an MPI call. The system, in fact, so that the buffer is the address, part of the address space it's exposing. Actually, the system might utilize internal buffers. It might not have as much space as you need for your message. So it might have to exchange data with the other process over the network in multiple steps, but you don't care about that. So that's what the MPI I receive does. It says, okay, I'm opening up part of my address space. The send tells the system where the data is that it wants to move, and it says where it's supposed to go. That is, whose address space it's supposed to be communicated into. And the MPI wait for either an I receive or a send is just saying, okay, when I want my program to stop until the system is done with these buffers and I can start treating them as my own. That means I can now read data out of that buffer and do something with it. And on the sender side, I can now reuse it and put stuff in there for the next message and so forth. So another thing about the non-blocking operations is that they're really much safer. In fact, the blocking operations that were the first things that you learned about when you wrote your first MPI program, send and receive, we thought about not putting them in the standard because they're so bad. And we had endless arguments, both in the meeting rooms and in the bar, over whether we should let them in. But people were so used to doing blocking sends and receives and not worrying too much about it because the programming libraries at the time had large buffer allocations in the system, and people weren't sending very big messages anyway because it was so slow, that we put them in. But they have a certain, they're dangerous in a certain way. And let me illustrate two bad things that can happen. They're not always bad, but they can be bad. So suppose that you were just going to exchange, two processes were going to exchange messages. That happens in a lot of programs. You're exchanging data with your memory. But let's suppose for the time being that the data that's being sent here, this one is just the destination rank argument. I've left all the others out. So let's suppose that the buffer that's one of the arguments to this send is actually quite large. It's larger than any chunk of memory that the system has in it. This send has to wait until it can get rid of that buffer. It has to give it to the system. Well, where's the system going to put it? It doesn't have room. So it waits for some memory to show up. Now that memory is going to show up when this guy does the receive, because when he does the receive, he supplies a big enough buffer for that incoming message. But he can't do that because this send is blocked because it needs this receive to supply the memory. So is this clear enough? Just a simple exchange, once the message is big enough, can hang. And the amount of the size of message at which this would hang is completely dependent on the MPI implementation and the operating system and the communication hardware. It's on the system. Some implementations might not block on a small message because the system has got some memory set aside for this purpose. In fact, Intel NX, which was one of the precursor systems for MPI, was very generous in its allocation of system memory. But another common system at the time was the one from Thinking Machines. It was called CMMD, I think was the name of that library. And there was a guy from Thinking Machines on the forum, and he says, we have no memory allocated for that. If you were to send 1 byte, exchange 1 byte, it would hang on that system. So yes, I say suppose it's a large message because most systems have some memory set aside, but they don't have to according to the standard. And of course we argued about whether the standard should specify that, oh well, at least there should be room for 10 128 byte messages. And then of course, even if it doesn't block, there can be a performance problem. If you do the send and the same thing happens, the send needs to unload the message somewhere and the system can't handle it, it has to wait till this receive happens because that's exactly what the receive does. It supplies the buffer. It supplies the exact space that the message is going to go into that's over here. And maybe the way your program works, maybe not even the way you think it works, but the way it does work, this receive doesn't happen for quite some time. And so you'll be stuck up at this send until it does happen and the transfer can take place. Those are things that you should be aware of when you're using the blocking send and receive. Might be fine, but there are these potential problems. So all I'm saying is here that the non-blocking communication solves both problems. So if instead of doing send receive, we post the receive, then do the send and do the wait and do the same thing over here, then you see what's happening. The The two receives, each application process has given the system the memory it needs to transfer, in small pieces if necessary, the data that's being sent. And the same thing happens with the performance situation. You can post the receive as early as possible, and then the send might complete quite quickly, and then you wait for it later. And that is, this wait is when you finally need to use it. In this particular picture, the receive side is where you're allocating the space. Well, there's also a way to do it on the sending side, and that's the relatively obscure MPI bsend, which we'll talk about a little bit later. But it's an approach to the same problem. It's just allocating the buffer on a different side. It's required of a correct program that there be enough that you receive into a big enough space to hold what gets sent. You can send a message shorter than the receives posted, but not longer. So that means when this guy does the receive, he's passing to the system the address of a space that's big enough to hold the message that's going to be sent here. So even if the system has to move it 1 byte at a time, it's guaranteed to have enough room. Another aspect of the non-blocking send and receive is the idea of overlapping communication and computation. That is, you do an I send or an I receive, and you do some computation before you do the wait. Maybe you can do that. Maybe the communication will take place and you'll get useful computation done at the same time. That might be your motivation for abandoning the blocking send and receive, is to achieve this overlap. That's not true that the MPI standard requires that overlap occur. That's up to the library, the operating system, the hardware, the system that I'm talking about. Use of the non-blocking communication is allow that to happen. It specifies exactly when and where it could happen. It allows that, but it doesn't require it, and it's not the real purpose. The real purpose is the buffer management that we were just talking about. So in fact, there are a lot of different things an implementation could do, implementation meaning the library, the operating system, the hardware, et cetera. There are a lot of different things it could do when faced with an I receive and a wait. In between the I receive and the wait, it could use a separate system thread that's dedicated only to message traffic or some hardware support in the NIC in order to do exactly what you would like, to move data, have that data be unloaded out of the buffer and sent at the same, or received at the same time other communication in your application is going on. Or maybe there are some other MPI calls. Maybe it doesn't do anything until you call MPI, because then you're giving it the thread to work with at that point. So a typical thing would be like an MPI test. Maybe it moves a bit of the message each time it does that. But it's moving during the time between the call and the wait, but not in parallel with that. Or it could complete the operation during the I send. If the message is short enough and there's buffer in the system, it can just take it. Or it could delay the whole thing until the wait, because you've promised not to touch that area until the wait occurs, so it could wait if that's what it wants to do. So all of those things are allowed, and your implementation will no doubt do the best it can. The use of the non-blocking send and receive does not require it to do it this first way. Just summing up now the various kinds of send, just to put them all together in one place. There are multiple types of send, but there's only one type of receive. So all of these go into the same receive, blocking receive or non-blocking receive. So the send blocks until the message is absorbed by the system. That doesn't mean it's received. You don't know. It just means the system's got it now, and you can go on and reuse the buffer. You've given it the data, and in some sense the system has given you the buffer back again, and you can use it however you like. So the MPI send does exactly what we've been talking about. It notifies the system where the data is, so there's no reason in that it shouldn't return pretty quickly. But you don't get to use the buffer because the system's using it for something. Then there are these three other sends that people don't use as much, maybe not as much as they should. The synchronous send blocks until the corresponding receive has occurred. So in the light of the discussion we've just been having, you could see why you might want that. So it's sort of like a non-blocking send, but it waits until that buffer on the other end has been supplied by the user. So there's a little communication must be going on underneath in the system. Then the rsend does another thing. What it does is take the responsibility for all this and give it back to the programmer. So it assumes that the corresponding receive has been posted. So that means it doesn't have to check and wait. It tells the system, you can fire this off because when it arrives on the other side, there will be a place to put it. I know because I've set up the program that way. So here's an example of how you might do that. Suppose you send a question and you're going to get back an answer. So what you might do is one guy says, I'll post the receive for the answer, and then before I send the question, then I'll wait for the answer afterwards. So then the other guy receives the question, we'll put it blocking receive here for simplicity, and then when he sends the answer back, he can use an rsend, which the system might optimize in some way. It might not, but an aggressive implementation will do so. It knows that the receive has been posted just because you're the person who wrote both halves of this. So you know that this send is being sent back to a receive that's already been posted before you could possibly have done the send. And then the bsend, the buffered send, is the one that allocates a local buffer so that you can get on with your work. Remember, someone has to be sure there's a place for this message when you send it before you can resume, before you can return from the send. So the blocking send lets you allocate a buffer that's big enough and attach it to this operation and then send. And then the bsend should return quickly because it's copied it in and the system knows where it is. The behavior of an erroneous program is not defined. It took us a while to figure this out, but we learned that specifying the behavior of a correct program was hard enough. Trying to say what kind of errors would be thrown precisely in what situations. Now there is a lot of error handling stuff in MPI already, but the standard in the behavior of these things, if you screw up, it's up to the implementation to handle it within the guidelines of how errors are reported. But the standard does not guarantee that some nice person will catch your error and point it out to you. So I just wanted to make one comment about collective operations. These are things that you may have already used. MPI provides lots of different communication patterns. Of course, so these are at least conceptually sitting on top of MPI. That's just a pattern of sends and receives that you could do yourself. Building them into the implementation allows for a lot of optimization that, first of all, you might not be aware of because there are a lot of pretty fancy algorithms for doing this. And also there might be special hardware support for collective operations that you want to tell the program, you want to tell the system always as much as possible as you can and let it optimize whatever has to happen. There are a lot of communication patterns. Some of them have built-in simple operations like an MPI reduce can add or multiply the data as it passes through the various nodes. There are multiple algorithms based, that is who sends who, how much of the message to whom in the middle of one of these operations. The multiple operations are based on different sizes and machine topologies and machine capabilities. And getting scalable algorithms for these is still an active research topic. Many implementations, including ours, choose a different algorithm for large messages than for short messages. Common feature of collective operations is they're always all called by all the processes in a communicator. In fact, that's sort of what I mean by a collective operation, so that the system, knowing that, can then organize the communication and computation that takes place as part of that operation. One performance note that's maybe worth mentioning, I sometimes hear people say that, well, the collective operations are too slow because I measured them and they're slow. Well, collective operations, many of them can't really get started or can't get started into the main part of what they do until all of the processes in the communicator have made the call. So what happens is that if the collective operations are going to have any hope of being fast, they all have to be called at about the same time, and it's very often the case that that doesn't happen. So this is just a load balancing problem. This computation before the all reduce took longer than these others, and if all you do is measure the time in the all reduces, you'll think the all reduce is slow, but the real problem is that this compute is too fast. It's not the fault of the collective communication that its average time is large if you don't give it a chance by starting them all at about the same time. That's not true of all the collective operations, but certainly of some. So far we've just talked about basic MPI-1 concepts. MPI-2 introduced, I would say, three big things and a bunch of odds and ends. So the three big things were dynamic process management, that's the MPI spawn and its related calls. Remote memory access, that's sometimes called the one-sided operations because you specify both, that is where it's starting and where it's going in the same call just on one side. Those are the put and get operations. And parallel I/O, MPI I/O, which is designed to be a portable approach to parallel I/O, and we'll say just a few things about that. So I'm not going to talk about, I think none of us are going to talk about dynamic process management. It's turned out to be not what people really want for large-scale computations. It's not universally implemented by the vendors, partly because the dynamic process management, that is the ability of an MPI program to start some other MPI processes and then maybe communicate with them, interacts with the operating system and the scheduler for the big parallel machine and so forth in ways that just message passing doesn't. And so, especially on large systems, you often don't find that. We're going to talk about the thread safety stuff in the hybrid programming part. We'll say just a few words about RMA and then a lot more about it tomorrow. Getting back to this idea of communication buffers in MPI as being just a limited way of opening up your address space, you can think of the MPI remote memory access as just making that window a little bigger. And in fact, we call it an MPI window. We have a window object on each process, and all those put together we call an MPI window. And what that does is each process says, okay, this is the bit of memory that I'm explicitly opening up to access by other processes. They can read out of it and they can write into it. And it's going to sit there for a while until I get rid of that window. So you're opening up in time larger part of your address space, presumably larger part, into sharing for the other processes. So you're still limiting it. It's just bigger now in both space and time than the communication buffers. But it's not conceptually all that different. It also separates the various things that are combined in the communication operations. So processes create windows. That's a collective operation. They don't all have to donate to the window the same amount of memory at the same place or anything. It can all be different. Then they can put things into the other process's window object and they can get things out of it. Those are all non-blocking operations. We argued for a while whether they should be I put and I get, but since there aren't blocking versions at all, we decided to leave it as put and get. There are accumulate operations that do some arithmetic on the fly. Since they're non-blocking, there has to be a synchronization so that you know that the operation is complete. That is, that the other guy has gotten the stuff out of your window object, or the put is completed. And there are multiple ways to synchronize. That makes the RMA operations, since they're non-blocking, a little bit more complicated than sending and receive. And there are really three ways: the MPI fence, the post-start complete wait, and the lock-unlock stuff. And we'll talk about this in some length tomorrow. Then I just want to say one thing about parallel I/O. The idea of MPI I/O is based on an analogy. This was Mark Schneer's idea, in fact. If you think about, just conceptually, writing data is sort of like sending data to a parallel process, only that parallel process is the file system. And reading data from the file system in parallel is a little bit like receiving messages from the file system. The idea is to try to exploit that process, and if you want to, no matter what you're going to do in defining a parallel I/O system, you're going to find that you need things like a way of describing non-contiguous data. That is, for efficiency, you'd like to take bits of memory that are in, bits of memory in your address space and perhaps write them into a file contiguously, or scatter them in some particular way, and you'd like the system to take care of that. Well, we already have a tool for doing exactly that in the MPI data types. They describe non-contiguous layouts in memory, and in MPI I/O, they're generalized to describe non-contiguous areas on disk as well. You need non-blocking operations because I/O is slow, And this is a place where there's a very good chance that you will be able to overlap communication and computation. And you'd like to have collective operations. You'd like to be able to say, well, I'd like to take all this data that's sitting in these different processes and write it out at once, possibly on the fly, joining up the various pieces in order to create contiguous blocks, which would jack up the performance of my I/O system. So a combination of data types and collective operations can fit very well together to improve parallel I/O, and there's a whole chunk of the course on parallel I/O later this week. And the MPI 3 stuff, we'll do at least a summary tomorrow of the topics that are in MPI 3.